Okay, let us continue our discussions. So we defined positive definite matrices and we looked at a few properties, right? So till now I think we have 4 properties of positive definite matrices, right? You can write a bunch of other properties. For example, if A is positive definite, then A is invertible. If A is positive definite, then A is certainly invertible. Why is that? Because we can look at it many ways. One way to say it is all the eigenvalues of A are positive, right? If you know that if a matrix is non-invertible, then it must have a 0 eigenvalue. We're talking about square matrices here, right? So if A is bigger than 0, then A is invertible. And in fact, you can go a step further and you can say that A inverse is also positive definite. Okay, why is this? Well, how do we prove this, right? No, this is one of those things that's a bit harder to prove from the definition, but much easier to prove by using the eigenvalue properties, right? So if A is positive definite, well, A is symmetric. First of all, by the spectral theorem it can be written as VDV transpose, where the diagonal entries of D are the eigenvalues, right? And importantly, the diagonal entries of D are all positive. Okay, yeah, diagonal entries of D are positive because A is a positive definite matrix, right? Now what is A inverse, right? So we know what A inverse is. So A inverse is simply going to be V D inverse V transpose. Okay, so for so what happens is the eigenvectors stay the same, but the eigenvalues get replaced by inverse. This was also one of the problems in your exam in the first segment, if I remember correctly. It's very easy to check that this is actually the inverse of A. You just multiply these two and you'll get identity, right? Just by using the fact that V is orthogonal, V transpose V is equal to identity, you will get A times A inverse is equal to identity. So they are indeed inverses of each other. Okay? So what are the eigenvalues of A inverse? They are simply 1 over the eigenvalues of A. So if the eigenvalues of A are positive, 1 over the eigenvalues are also positive, and that's why all the eigenvalues of A inverse are positive, and that's why A inverse is positive definite. Okay. Once again, this is a lot like how positive numbers behave. If you have a positive number and if you take its reciprocal, you still get a positive number, right? This is a property very similar to that. Well, you can also write, for example, A to the k is positive. A to the k is positive for any integer k. Okay, so A square, A cube, they'll all be positive because for the same reason, right? A to the k will actually be V times D to the k times V transpose. Okay, so that's that will actually say that all the powers of A are also positive definite. Okay, you can also take a square root of a positive definite matrix. So A to the half is well defined. You can write A to the half as V times D to the half V transpose. Okay, so A to the half, the square root of A, is actually A times V times D to the half times V transpose, because what happens when you multiply A to the half with itself is, for the same reason, you'll get V D to the half V transpose times V D to the half V transpose. Well, these two terms will simply cancel off each other, and then you're left with D to the half times D to the half, which is just D, and you'll get V D V transpose, which is A. Okay, so in some sense, A to the half here is a matrix which, when multiplied with itself, gives you A. That's by definition the square root. Correct? That's why we write A to the half here, right? So A to the half is a square root. So positive definite matrices have a square root. Okay. Now this was possible for us to write because I could write D to the half here. Okay. And the reason I could write D to the half is basically because the diagonal entries of D are all positive. Okay. So what is D to the half here? D to the half here is simply a matrix with eigenvalue with diagonal entries square root lambda 1, square root lambda 2 up to square root lambda n. Okay, and these square roots are all well defined because the lambdas are positive. Okay, and the lambdas are positive because A is positive definite. Okay, so what I'm trying to say is that if A is positive definite, then all its eigenvalues are positive. Then I can simply take the square root of those eigenvalues and define D to the half, and then I can use that definition to construct A to the half. Okay, so all positive definite matrices have a square root, just like all positive numbers have a square root. Okay, Similarly, you can talk about if A is positive definite and B is positive definite, then A plus B is also positive definite. Okay, just like positive numbers, right? If you take two positive numbers and add them, you get a positive number. Okay, so if A is positive definite, B is positive definite, then A plus B is positive. How do we prove this? Well, the simplest way to prove this is from the definition, right? So we can just construct the quadratic form of A plus B, x transpose A plus B x, and we see just by, we have done this in the previous lecture as well, x transpose bx, both these terms here are positive, right? So the sum is also positive. So A plus B is positive. No matter what x is, the sum here is going to be positive, and hence it's a positive definite matrix. Okay, you can also prove this from one of the results we discussed in the last class. Lambda min A plus B is greater than or equal to lambda min A plus lambda min B. Right? If you remember, we had this. Again, this comes from the Rayleigh quotient theorem applied to this equation. Right? From here you see that lambda min A is positive, lambda min B is positive, because A and B are both positive definite. So lambda min A plus B is also positive, and hence A plus B is positive definite. Okay? That's another way you can see this. Right? You can also say if A is positive definite, then alpha A is positive definite. Okay? For any positive alpha. Okay? This is also quite straightforward. Just from the definition, the quadratic form just gets multiplied by alpha, right? Sometimes people combine these two, and you can write it as if A is positive definite and B is positive definite, then alpha 1A plus alpha 2B is positive definite, where alpha 1 alpha 2 are positive numbers. Okay, right? So if you take in some sense A and B are positive definite, you take their combination, but while taking the combination, make sure you only use positive coefficients, then the sum is also positive. Okay, very good. Now one thing I do want to point out, even though I've been saying that matrices, all these properties here are very similar to properties of positive numbers, right? For example, here this one is just said, if you add two positive numbers, you get a positive number, right? Same thing is happening for matrices. You have to be cautious that not all properties of positive numbers translate to properties of matrices. For example, one important property of any positive number is that or any number rather, is that it's either positive or negative, right? Any number is either positive or negative, right? But that's not the case for matrices, right? A matrix doesn't have to be either positive definite or negative definite, right? It could actually be indefinite. Number 6. Okay, if A is positive definite, so is P transpose AP for any P. Okay, so if A is positive definite, so is P transpose AP for any P with full column rank. Okay, or any P with linearly independent columns. Okay, full column rank essentially means linearly independent columns. Right? A is bigger than 0, then so is P transpose AP, and there is no restriction on the size of P. P could be like a skinny matrix as well. Okay, of course P can't be fat the way I have written it, right? The reason why P can't be fat is because if it is fat, then it cannot have linearly independent columns, right? So P is either square or skinny in this context, right? So in that case, P transpose AP is also positive definite. Okay, how do we prove this? Well, you start from the definition, right? So let's construct the corresponding quadratic form for P transpose AP. This is going to be x transpose P transpose APX, right? Now that's going to be equal to PX whole transpose APX. Okay, so now this here on the left is a quadratic form for this matrix P transpose APX, right? What you have on the right is a quadratic form for A with this as your variable, with a changed variable. Okay. Now what do you know about this quadratic form? A is given to be positive definite, so no matter what quadratic form it is, so variable transpose A times variable is always positive, right? So this is always positive, unless px equal to 0. Okay, unless px equal to 0, correct? If px equal to 0, then it will be positive. Okay, now you're given that p has linearly independent columns. So is it possible that px equal to 0? Right? Since the columns of p are linearly independent, if you write px equal to 0, recall that px is a linear combination of the columns of p. The only way px can be 0 is if x equal to 0. Okay, right? Because the columns of p are linearly independent, and px equal to 0 is only possible when x equal to 0. Right? So what do we have in summary? We have that this quadratic form p transpose apx is bigger than 0 unless x equal to 0. Okay, and when x equal to 0, then this quadratic form is clearly 0. Right? So this is precisely what is the definition of positive definiteness, correct? So which implies that p transpose ap is positive definite. P transpose ap is bigger than 0. Okay, so that is one of the very important properties. In fact, the property that I talked about for submatrices is actually a consequence of this. Okay. Okay. Anyway. Okay. I hope this is okay for everybody. Okay. And then let me look at another property. So if you have a matrix A, and suppose I know that A is positive definite, and I now suppose append zeros and construct a new matrix. So here A is n cross n matrix, and I construct this full n plus 1 cross n plus 1 matrix. Okay, so n plus 1 cross n plus 1 matrix by simply adding another scalar here, alpha. Okay, and the new row. So this is the new row that I add, and this is the new column that I add, right? And the new row and column that I add is all zeros except for the diagonal entry, which is alpha. Okay, diagonal entry is alpha, everything else is 0. Okay, so if A is positive definite, so let's call this B, right? If A is positive definite, then if A is positive definite and alpha is positive, then B is positive definite. Okay, if A is positive definite and alpha, here is just a scalar, alpha is positive, then B is positive definite. Okay, so how do we prove this? Once again, to prove that B is positive definite, you have to construct the quadratic form for B, right? So when you do x transpose Bx, right, this B matrix being a block matrix, let's actually rewrite even x in terms of blocks. Okay, so let's write it as the x1 block, x2 multiplied with a0 0 alpha multiplied with x1 x2. Okay, now we expand the whole thing out. So here x1 here is n length, so x here is, remember, n plus 1 length, right? N plus 1 variables. X1 is n length, x2 is 1 length, so x2 is just a scalar here. Okay, fine. So we expand this, you will get x1 transpose ax1 plus x2 square times alpha. Okay, now I know that this quantity is positive. Okay, this quantity is always non-negative. In fact, it's 0 when x1 is 0, otherwise it's positive, right? And this quantity is also always positive unless x2 is 0. So this whole thing is positive, and the only way the whole thing will be 0 is if x1 is 0. The only way the whole thing will be 0 is if x1 is 0 and x2 is 0. Okay, so basically this whole thing is positive unless x1 equal to x2 equal to 0, which is again the definition of positive definiteness. Okay, so x transpose bx is also so B is also positive. Okay. Okay, by the way, let me just leave this as a question to you guys. What about a converse to 7? Meaning that if suppose I know that this matrix B is positive definite, how can I conclude that A is positive definite and alpha is positive? Or can I conclude that A is positive definite and alpha is positive? Right? Well, A is a principal submatrix of B. So if B is positive definite, then A is definitely positive. Alpha is a diagonal entry of B. So if B is positive definite, then alpha is definitely positive. Okay. So converse to 7 is also true. Okay. Right. Okay. For that matter, you could have appended A here instead of just appending it with a scalar here. You could have appended it with another diagonal matrix. So you could also have something like this: A0 0 C. Call this as B. Right. If A and C are positive definite, then B is also positive definite. Okay. can check this in exactly the same way that we did this thing here. Okay, if A is positive definite and C is positive definite, then the block matrix obtained by appending A and C along the effectively like the block diagonals, right? That is also positive definite. Okay. So these are some of the key important properties of positive semi-definite matrices. Let me make one very quick definition. Positive semi-definite matrices. Okay. So here we attached semi to definite, right? So these are just like non-negative numbers. Okay, positive definite matrices are like positive numbers. These are like non-negative numbers. Okay, so in particular here we say that A is positive semi-definite. We'll use the shorthand PSD for now. If the quadratic form x transpose AX is greater than or equal to 0 for any x. Okay, we don't have to write x not equal to 0 now because that's included here anyway, right? It's positive semi-definite if x transpose AX is always greater than or equal to 0, no matter what x is. Okay, we use the notation A greater than or equal to 0 to mean A is PSD. Okay, A greater than or equal to 0 means A is positive semi-definite. Okay, now the thing to note here is we have a similar theorem for positive semi-definite matrices. A greater than or equal to 0 if and only if all eigenvalues of A are non-negative. Okay, in particular this means that we allow some eigenvalues to be 0. They can be potentially 0. Okay, some eigenvalues can be potentially 0. Okay, but they cannot be negative. For a positive definite matrix, all eigenvalues must be positive. They cannot even be 0. They have to be positive. Okay, for a positive semi-definite matrix, all eigenvalues have to be greater than or equal to 0. They can potentially be 0. Okay, a positive semi-definite matrix need not be invertible. Okay. It could have a 0 eigenvalue. Okay, it could have a 0 eigenvalue. Okay, so most of the properties that we discussed till now will work even for positive semi-definite matrices without much change at all. Most of the properties that we discussed will go through even for positive semi-definite matrices.